All right, so today we're going to look at 1.5. It's on quadratic functions, and specifically how we can transform them. When I talk about transforming something, we basically mean like moving it up and down, moving it left and right, or stretching it up and down, or stretching it left and right. Those are transformations. So the equations that we're going to be looking at are going to look something like that today. Ax squared plus bx plus c. Okay? That's a quadratic because the highest exponent there is a what? Yeah. It's a 2. Yeah. So any equation that's a polynomial and the highest exponent is a 2, that makes it a quadratic. The a, the b, and the c, again, are real numbers. We're not dealing with like imaginaries or anything like that. There's only one thing that you can't plug in for a. You can't plug in 0. Because what would happen if a was 0 and you multiplied x squared times 0? It would cancel out. So all that would be left now is bx plus c. That's a line. Okay, if you wipe out the exponent of 2, you're down to a line instead of a quadratic. Okay, so you can't have a be 0. B and c could be 0. That's fine. All right, so let's graph y equals x squared. Just kind of see what that looks like. So y equals x squared, that's the simplest type of quadratic that you can graph. And it looks like a U-shape. Does anyone remember, it's not really called a U-shape, does anyone remember what that shape's really called? Yeah?
Parabola.
Yeah, that's a parabola. Now, watch what happens if, instead of graphing x squared, I graph negative x in parentheses squared. I want you to watch what happens when I put a negative on the inside. So there's my blue graph. There's my red graph. What's the difference? Yeah?
Because you're squaring the actual negative number, which is negative times the negative, which is positive.
Mm-hmm. So what's the difference between the blue one and the red one in terms of the actual picture? They look the same. Something did happen. What happened there is what's called a reflection. But since the parabola is drawn right over the y-axis, that negative causes it to flip over the y-axis. But parabolas is symmetrical, so flipping it that way, you don't notice. If you flip it the other way, you would notice, because then the parabola would open downward. Right? But putting in that negative on the inside, it causes what we call a reflection over the y-axis. Okay, if I did that with something you could actually see, like let me do it with a letter. That's a reflection over the y-axis. And the letter B is not symmetrical, so you can actually see that I did it. Another name for that is you can also call it a horizontal reflection because it's flipping left to right. So either way, that's what the negative does. Parabola is not a good picture to see that on because you can't even tell. So in this problem, I don't think I said this quite exactly, but the y-axis is what we call a line of symmetry. And the low point, right there, that is called the vertex. The vertex doesn't have to be the lowest point. It could be the highest point. If you took your parabola and you flipped it, then the vertex would be at the top. Any question on what the vertex is? Yeah.
What if the graph was like flipped upside down? Would it still be like where it comes together, or would it then be like the 2 points at the bottom?
So if it was flipped upside down like this one, it would be right there.
Okay.
Yeah. Because remember, there really isn't a bottom to it because these are just going to keep going down forever. These two sides just go to negative infinity. All right, so what I want to do now is I want to look at what happens if we change that number. That's the number in front of the x squared. Okay, so I'm going to graph it one time as a 1/3, and then I'll do it another time as a 2. Okay, so I'll leave y equals x squared. Okay, that was the original. And let's put in 1/3 x squared. That's one way you can type 1/3. That's how I do it. And 2x squared. Okay, so that's the original. Here's the 1/3 x squared. And then the 2x squared. Okay, and the way we described what happened here is we talk about it kind of either being squished down or being stretched taller. Which graph there, the red, the blue, or the black, looks like it was stretched the tallest? The black one, yeah. Think of them as all being glued down at the origin. If you took the sides and you pulled up on it, right? Like if you had like Play-Doh and it was glued down and you pull up on it, what's going to happen? It's going to get thinner and skinnier as you pull up on it. If you take and you start to squish it down, what's going to happen? It's going to spread out sideways. And that's what happened with the red one, right? It's like it got pushed down and it started to spread out sideways. So changing this number in front causes the graph to either stretch vertically or compress vertically. Which one happens depends on if the number is bigger than 1 or a decimal between 0 and 1. If you put in a number bigger than 1, 2, 3.7, whatever you want, anything bigger than 1, that's going to cause the graph to stretch. The bigger you make the number, the more it's going to stretch. Okay, so here's one in pink that's stretched out even more vertically. Right, so the bigger you make the number in front of x squared, the more of a stretch you get. If you put in a decimal or a fraction between 0 and 1, that's going to cause the graph to compress, and that's why it looks like it got wider. So what would be another number between 0 and 1? Yeah? 0.5. So if I do 0.5x squared, that's going to be, it's going to stretch it a little bit. It's not going to squish it as much as the 1/3 did, okay? So it's going to be kind of in between. And you can see it's in between some of the graphs. So it squished it down a little and made it wider, but not as much. If you really wanted to squish it way down, you could do something like 0.1x squared. Okay. That orange one is going to really be squished, so it gets a lot wider. Okay. Any question on what changing the number in front of x squared is? All right. So now we've changed the number. Let's change the number and make it a negative at the same time. When I did a negative earlier, did anyone remember what, we couldn't see it, but I wrote down what happened? What did the negative cause the graph to do? It reflected it. That's when we put a negative on the inside in parentheses. Okay, right here. What we're doing now is we're going to put a negative out in the front. So we're still going to have some kind of reflection, but it's going to be a little bit different. Okay, I'm going to get rid of all these other ones, and I'm just going to graph the first one. So I've got x squared, and I'm going to do negative x squared. That's enough that you can see what's going to happen. So that's the original. And here's the one with the negative in front. What did that negative cause the graph to do?
Flip.
Yep, flip how?
Like a reflection of the X.
Yeah, that's a reflection over the x-axis. Okay, and that causes the graph to open downward. So when we talk about transformations, like if you had to describe the transformations in this problem, there's actually two. There's the 1/3. We explained what that does on the previous page. And there's the negative. Those are two separate things. So this one has two things. This one also has two things. That's a vertical stretch by a factor of 2. And that's causing a reflection over the x-axis. So just make sure you describe those as two separate things. Here, there's only one. There's no vertical stretch because the number in front of x squared is still a 1. But there is a negative. So it will cause it to reflect over the x-axis. Right, so let's look at a problem and just see if we can describe what's happening. So the question is, how could you get this if you started with that? Well, the first thing is to identify how many things you would need to do. How many transformations are happening in this graph? Right here, yeah, Ricky?
2.
Yeah, there's 2. The 5 is going to do something, and we can look that up right here. And then the negative is going to do something else, and you can look that up right there. Let's start with the 5. What kind of transformation is this 5? What is it going to do to the graph? Yeah?
Vertical stretch.
Vertical stretch. So the way we write this down is we say it's a vertical stretch. But then you just tell me by how much? By a factor of 5. That's the first thing that happens. It's a vertical stretch by a factor of 5. So it's going to get like 5 times as tall. Okay. Now the second thing is that negative. What did we say that this negative is going to do to the graph? Yeah.
It's going to reflect it on the x-axis.
And that's exactly what you write down. Reflect over the x-axis. So if you had this graph and you wanted to turn it into that one, those are the two things you would do to it. Stretch it 5 times as tall, and then take that whole thing and flip it. Okay, so any question on just describing the transformations? Okay. Now, let's look at what happens. Instead of putting a number in front of the x squared, I want to add or subtract a number on the end. Let's see what that does. This is not going to stretch it. It's going to do something else. Anyone think they know how x squared is going to compare to x squared plus 2? What do you think the plus 2 is going to do? Yeah?
Is that going to like move it over
Which way?
on the x-axis?
Okay, you could move it on the x-axis. That's one option. Or what other way could it move it?
I could move on the y-axis.
Could move on the y-axis. This one does move on the y-axis. Do you think the plus 2 is going to move it up 2 or down 2? Yeah, it does. It moves it up 2. That's the original, and that's the new one. And you can tell it's gone up 2. What do you think if I did the minus 3? What would that do? That would move it down 3. Yep. So let's answer that. So how do we get, so to get y equals x squared plus 2, we would shift, that's the word you use, it's called a shift. Shift y equals x squared up 2. Take the original and move it up 2, and then you'd have the first one. To get y equals x squared minus 3, what did we say is going to happen to the original one? It's going to take it, and the minus 3 is going to
Down 3.
It's going to move it down 3. Okay, so both of these are called translations. Okay, that's what's happening here. So when you're doing a shift, nothing is stretching. You're just taking what you have and you're just moving it, you're sliding it somewhere else. Okay. That's called a vertical shift. The reason it's called rigid motion is because it's not being stretched or distorted. It's just taking it and sliding it somewhere. Okay, so we have to remember which way this number at the end is going to move it. If that number is a positive, right, it's going to move it up. So if this is a positive, it moves up. If it's a negative, it moves down. Notice I put down absolute value of k units because let's say you had something like the one we have up here, y equals x squared minus 3. You wouldn't say that this moves down negative 3. It can go up 3 or it can go down 3, but it can't go a negative amount. So when you describe the amount of movement, that's always a positive number. If you want to say down, then you can say down 3. If you want to say up, you say up 3. But don't say down negative 3. That doesn't make sense. So in general, any kind of adding or subtracting, if it's a negative number, that's going to move it up and down if you add or subtract it on the end. So just to kind of compare that to what I have over there, that's adding and subtracting again, but it's not on the end. It's inside the parentheses. So adding and subtracting on the end moves it up and down. What do you think adding and subtracting inside is going to do?
Left and right.
It's going to move left and right, but it's not the way you would expect. If I put in minus 3, you might think minus 3 is going to go left 3 because the negative numbers go to the left. It doesn't work that way. So let's type in x minus 3 and square it. So the one in blue, that's going to be the original. And instead of moving 3 to the left, the red one is going to go 3 to the right. So minus a number moves it right, plus a number is going to move it left. So that's a little tricky because it's backwards from what you would think. So on the left, those are vertical shifts, moving left and right. What do you think those are called? Yeah,
Horizontal shift.
those are horizontal shifts. Again, these are both what we call rigid motion transformations because you're not distorting anything. You're just taking what you have and sliding it left or right. All right. If the number that you put right okay. So if the number that you put right here is bigger than 0, if you put a plus number, right, it's going to move it to the left. So it's the opposite of what you would think. If you put a number there that's smaller than 0, like x minus 6, that's smaller than 0, it's going to move it to the right. But don't say that it would go to the right negative 6 units. We just say it goes to the right 6 units. Any question on what the h, I call it h, what this h value is doing? Positive goes left, negative goes right. And again, you can put that on a reference sheet if you want for the test. But somehow you got to remember it. Let me put the original one back up, just y equals x squared. Where does it look like the vertex is in that picture?
0.
0, 0. Yep, it's at 0, 0. Which way does h move the vertex again?
To the left.
Left or right? And which way does k move the vertex?
Up and down.
Up or down? Yep. So if we want to figure out where our new vertex is, there's a formula that we can use after we've moved it left and right. And using the formula, it's negative h, comma, k. The reason that has a negative in front of it is because, remember, moving left and right is the opposite of what you would think. So if h is a plus 3, it's actually going to move it left 3, which is in the negative direction. K does exactly what you would expect. Positive is up, negative is down. That one's normal. Okay. But that's the formula for how you find your vertex if you shift it left and right. Just, it's the opposite for left and right. And K is the up and down. And the line of symmetry is also going to move. Here's your parabola. There's your line of symmetry. If I take that parabola and let's say I shifted it up, does shifting it up change the line of symmetry? No. How about shifting it down? No. That's why K has nothing to do with the line of symmetry. The only thing that can change the line of symmetry is if you move it left and right. And H is the value that moves it left and right. And the reason it's x equals is because x equals is the equation for a vertical line. And that's exactly what the line of symmetry is for a parabola. It's always vertical. All right, so let's look at a problem and see if we can figure out the vertex and the line of symmetry, and I will leave the formula on the board. Okay, to figure out the vertex, what I usually do is I don't even remember the formula. I just think of the two transformations in my head. Plus 2. Which way is that going to move everything? That's going to go left 2. So what I do is just write that down off to the side. Left 2. And what about the minus 3?
Down 3.
Down 3. So think of where the vertex would normally be. It would have been at the origin. If you start at the origin and you go left 2 and down 3, what coordinate would you be at?
Negative 2, negative 3.
-2, -3. The opposite of that number on the inside. That's why it says the opposite of h. And then the k, I just copied down. Okay. Now my line of symmetry. What letter is always by itself on the left side when you write the line of symmetry? It's always x, because x means it's a vertical line. And it's x equals, it's the same number that you just put right there. So what's the number that we put as the first number for the vertex? -2. It's the same number. Okay. That's how you find the vertex and the line of symmetry when you shift it. Okay, so I think it's helpful just to write these two things down. And it makes it a little easier to think about. Questions on that? So let's look at describing the transformations here. Now, I wrote in parentheses that the order makes a difference. And that's because when you are doing transformations, it's kind of like PEMDAS. if you do arithmetic in a different order, you get a different answer, right? Think of like 2 times 5 plus 3. If I do this properly, what do I get for the answer? I get 13. I do multiplication first. 2 times 5 is 10. 10 plus 3 is 13. Now, if you do it the wrong way, let's say you do 5 plus 3 first. What's that give you? 8. And what's 8 times 2? 16. That's not the same thing. So we have to decide on what way we're going to do it. And the way we decide is we have an order of operations. As long as everybody follows that same order, then we're okay. It's like everybody, stop on red, go on green, we're good. But if we don't follow the same order and then people decide to do different things, then we get different answers. So when we are doing transformations and we have to list them, that's the order that we will follow. And if you're looking at that and you're wondering, well, where would like horizontal stretch come in? We didn't really do that with parabolas. We will later on. But a horizontal stretch would come in right here. You do all your horizontal stuff first. You do all your vertical stuff last. For this lesson, you only have to worry about 1 through 4. So first thing you deal with is any horizontal shifts. Then technically it would be horizontal stretches, but we're skipping that. Then the next thing we would deal with is the vertical stretches, or shrink, compression. Depends on if the number is bigger than 1, smaller than 1. Then if that number that's doing the vertical stretch and shrinking has a negative in front of it, that will cause a reflection. And these are all if necessary. Okay, not every problem is going to have every transformation in it. And then the last thing is the vertical shift. All right, so first thing, let's just look at f of x, right there. How many transformations are in that problem?
2.
Just 2. So we're going to start with number 1. If we don't have it, we skip it. Go to the next one. Horizontal shift. That's when you have a plus or a minus inside the parentheses. Do we have a plus or a minus inside parentheses here? No. It's just 5x squared plus 4. This problem doesn't have the horizontal shift. Okay. Do we have a vertical stretch or compression? Yes. Which number is going to cause that to happen?
5.
The 5. Yep. So for the 5, vertical stretch by factor of 5. Okay, so we've got that. Do we have a reflection or a flip over the x-axis? No. If we were to have that, there would have been a negative in front of the 5. Okay, so skip the third one. Do we have a vertical shift? Yes. Which number is causing the vertical shift?
4.
The 4. So can you tell me which way and how much?
Right, 4.
What kind of transformation is it? It's a
Outward.
vertical.
Up.
So shift up 4. There you go. So there's the 2 transformations for that one. All right. Let's try this one. So it's right there. So just take a look at it for a second and see if you can figure out how many transformations there are. How many do we think there are? Yeah, Ricky? 4. Yes, there are 4. Every one of them is in this problem. since every one of them is in the problem, I'm just going to ask which number there is the horizontal shift. Yep, and which way is a -1
Right.
going to move the graph?
Right.
Yep, so that's the first thing. Shift right 1. Okay, the next one, we have a vertical stretch. Which number is going to cause a vertical stretch? 3. And how do I write it down? Vertical.
Shrink.
So that's a stretch because remember this number is bigger than 1.
Oh, yeah.
So that's the letter that we called A.
So you don't count the negative?
We do, but not yet. That's going to be another transformation.
Reflection.
Yeah, that'll be the reflection after. So what were you saying? Vertical stretch. And what else do we have to say? Right. By factor of 3. Now that negative in front of the 3, that's a different transformation. It's not part of the vertical stretch. That does something else. What does the negative in front of the 3 do? Yeah. Yep. Which way?
Down.
So over.
The x-axis.
Yeah. So we're going to say it reflects over the x-axis. And which number causes the vertical shift? And then which way does it move it and how much? Yep. Shift up 4. Yep. Now, all these problems that we've been doing are in what are called standard form, and that's the only format I will ever give them to you in. If you're wondering, well, what would it mean if it wasn't standard form? Well, let's say you had something like this. Right? It's easy to tell the transformations because it's in standard form. This -2 is going to move it 2 to the right. This -4 is going to move it 4 down. If somebody took that and actually FOILed it all out, right? And they had x squared minus 2x minus 2x, and then -2 times -2 is +4. And then you have this -4, and the 4's would cancel. If you write it like that, that's the same thing. Like if you graph that on the calculator and graph that, they'll look the same. The problem is, looking at this, I can't tell my transformations at all. This one had 2 units being shifted to the right. Well, where's the 2 now? It's gone. I can't even tell that there was a 2 ever in the problem. So if you take something that's in standard form and you do it all out, that's going to mess you up. You don't ever want to do it all out. You always want to leave it like that. Okay. Yeah?
Would we have a problem that only shows that one?
No, I'm always going to give you the problems in standard form. Right? I'm not going to, because if I gave it to you like this, then what you have to do is figure out how to work it backwards and change it back to that. Right? And that's just not really something we're going to talk about. Okay, so your problems will always be in standard form. So again, we're not going to talk about what to do if it's not in standard form. Okay. All right. So the last thing, when you have a parabola, it looks something like that. How many times does that graph cross the x-axis? Yeah, it actually doesn't really cross it. It kind of comes down, it touches it, and then it goes back up. Wherever the graph touches the x-axis, that's called the 0 of the function. It's where the graph touches the x-axis. Is there, besides one time, is there a different number of times that I could somehow draw a parabola and have it cross the x-axis more than once or less than once? Yeah, how could I draw a parabola differently? And have it cross either more than one time or less than one time.
Vertical stretches.
Well, let's say you take that one, and what could you do with this one? I could just take this, and where could I move it so it crossed more than one time? Yeah.
You can shift it down.
Yeah, I can just shift it down somewhere, and now it crosses the axis twice. So when you draw a parabola, it could cross the axis twice. It could just come down and touch the axis once. Is there anything else that could happen? If I moved it up, what would happen there?
No, like you could flip it and then move it up.
Okay, yeah, you could flip it and move it up, and that could potentially also cross twice, something like that. So it could cross once, it could cross twice. I'm looking for, is there anything else that could happen?
Could touch none at all.
Yeah, it might not touch at all. Like look at the U shape that's up there. Or take the one Veronica just suggested and move it down. So there's 3 different things that can happen when you draw a parabola in terms of how many times it crosses. 0, 1, or 2 times. So quadratics can cross the x-axis 0, 1, or 2 times. Again, where it crosses, that number is called the 0. If you want to think about it like algebraically, this isn't a quadratic, but it's just easier to think about. What number could I plug in for x right there? And if I plugged it in, the answer would come out to 0.
2. Oh, wait.
Negative 2. So negative 2 is called the 0 of that function. It's the number you could plug in for x, and the answer would come out to 0. That's what this is saying right here. It's something you can plug in, and it equals 0. Quadratics, it's a little harder to find the zeros. Usually you've got a factor to use quadratic formula, but linear, non-quadratic problems, it's easier to find. If you want to quickly figure out how many times it crosses the x-axis, this calculation will tell you. It won't tell you where it crosses the x-axis. It'll just tell you, do you have this case? Do you have that case? Or do you have that case? Does it cross? Not at all, once, or twice. And the calculation you need to do is b squared minus 4ac. Okay, that's part of a formula. Does anybody recognize what formula that's from?
Quadratic formula.
It's part of the quadratic formula. It's not the whole formula. If you want to know the exact answer to the problem, you got to do the whole formula. But if you just want to know where it crosses the x-axis, I mean how many times it crosses, we do this calculation. If b squared minus 4ac is less than 0, if this comes out to a negative number, it will never cross the x-axis, and your graph is going to look like this one. If b squared minus 4ac is exactly 0, then your graph will come down, it'll touch the axis, and it'll go back up. It'll look like that one. And lastly, if b squared minus 4ac comes out to be a number that's bigger than 0, it's going to look something like that one. Let's just make one up. 2x squared plus 3x minus 5. I just want to know how many times it hits the x-axis without sketching it. What's A in that problem? 2. What's B? 3. And C? Negative 5. Yeah, I'm going to take the sign to the left that goes with the number. All right, so let's see what b squared minus 4ac is. What's b to the second power in this one? 9. Minus 4 times, what's a? 2. And what's c? Negative 5. Well, when you multiply a -4 times a -5, what's going to happen when you have a minus? A minus.
Turn positive.
Right, that's going to turn positive. And I have 9 plus 4 times 2 times 5. I don't care what that is exactly. All I care about is that going to be less than 0, equal to 0, or more than 0? That's going to be more than 0. So if I draw this, it should cross the x-axis how many times? Twice. How come? Right, because this is going to come out to 8 times 5 is 40, plus 9 is 49. It's going to come out bigger than 0. So let's just see what it looks like. But I guarantee you, it will cross twice. There's once, there's twice. Okay, it doesn't tell me where it crossed, but it did tell me it crossed twice. Any questions on that? All right, so that is section 1.5. So let me see which page. All right, so we're doing that one. So page 56. 1, 7, 10, 18. And then 22, 28, 33, 44, and 40. So 9 questions. If you had trouble with last night's homework and you were able to get that done, just show me tomorrow, and then I'll check that out. Reminder, tomorrow will be our last lesson for the week. Thursday will be a review day, and then Friday will be our test, just on the material from this week.